So can I get a show of hands of who's already paid their taxes? Is anybody planning on cheating on their taxes? Okay, so the talk today is going to be about using machine learning to identify tax evasion. A little bit about me. I got my master's in geophysics from Scripps Institution of Oceanography and my bachelor's at UC Berkeley in geophysics as well. And then for a brief period of time, I did a bit of science journalism. And now I'm a data scientist at H2O. So what is money laundering? Basically, it's just making dirty money look clean. And the way that it works is that you need to get your money into a bank without getting noticed, and then you need to get your money out of the bank without getting noticed. So pretty simple, right? So there are three stages. There's the placement stage, in which you need to figure out how you're going to get your money into an individual bank. So this can be kind of tricky because you might need to actually hire a couple people to slowly deposit in money, or you have the possibility of getting caught. The next step is layering, which is how you figure out how to get your money into multiple banks, potentially across multiple countries, again without getting noticed. And then finally, the best stage is when you get to get your money out. But again, you don't want to get noticed, so maybe you'll buy a boat or a house or some fancy jewelry, whatever, so that it's not too suspicious. This is a really fun fact. There's this island off the coast in the Pacific called Nauru, which used to be very famous for money laundering. And there's a great article in the New York Times about how Russian criminals managed to money launder $70 billion through the shell bank in Nauru. And there's also a really great This American Life story about it. So why is money laundering hard to catch? Well, for one thing, a lot of transactions happen in cash, and so you can't really keep track of it. And then the transactions that do happen, if people do successful layering, they're hard to untangle. It's hard to figure out like where the money originally came from. The systems that we have in place, a lot of them are rule-based, and they only have a certain time span in which they can remember transactions. And so if you're patient and you can figure out how long you have to wait, you can get around those systems potentially. And then the last thing is that people figure out what the rules are and they get around them, or they pay off people. So could machine learning be something that's helpful? So people are pretty excited about machine learning. There have been machine learning algorithms that have beat the master chess player, beat the master Go player, and now we have self-driving cars, still work in progress, and Google Translate has gotten significantly better. And then this is an analogy I really like. So when you're trying to think about why you should use machine learning instead of a rules-based system, think about how you would teach a child to identify an animal, right? Like, you're not going to tell a 4-year-old, hey, anything with 4 legs and a bushy tail is an animal, right? Because there's going to be problems. Like, what about, I don't know, kangaroo or a flamingo? So what you'll do is you'll take the kid on a walk, you'll point out animals, maybe you'll go on a nature hike, and eventually they'll learn to identify a dog in any context, whether it's just a fluffy dog next to you or in a towel. So far, the main points of why you'd want to use machine learning over a rules-based system is that you don't need to specify what the rules are. The machine learning algorithm will actually learn from the data. So instead of having to hard code, do this and then do that, you can just let the machine learning algorithm look at what the patterns are in a labeled data set. And the machine learning algorithm can actually learn not only what the rules are, but maybe what the thresholds are and the cutoff points. And it's also not deterministic. So it's giving you sort of the probability that something's going to happen. So now I'm going to give you just a little background about H2O, because maybe if you do want to use machine learning, H2O would be a great way to go, right? So H2O is a distributed in-memory platform. We have a bunch of different algorithms you can use. It's open source, so you can just download it. And if you're a fan of Python or R, we have great APIs that you can use. And because it's distributed in memory, you can use it on huge data sets. You don't need to do sampling. H2O is also built to integrate with Spark and Hadoop, but if you just want to use it on your laptop, that's fine as well. The algorithms that we have are GLMs, decision trees like random forest, gradient boosted machines. We have neural nets, k-means, autoencoders, so there's just a whole toolkit that you can take advantage of. And then just a super fast refresher, because I'm going to be focusing on random forest. So the way random forest works is it builds a bunch of different decision trees, and then it just averages them. So you're passing in your data, It figures out how to split it up, it averages it, and then it actually outputs predictions. So in this case, like whether somebody would be suspect or innocent. So now for the tax evasion use case, how regulators deal with tax evasion. So in 1970, there was the Bank Secrecy Act, and maybe most of you know this, but the bank will actually report certain transactions to the IRS or FinCEN, depending on what you're doing. And the rule that I'm going to focus on today is the idea of regulators getting this information. So whenever you do a transaction that's over $10,000, that'll actually get flagged, rolled up in a report, and sent to the IRS or FinCEN. So then the question becomes, what are we going to do with all the transactions that are below $10,000? Well, they don't get flagged. So this is where structuring comes in. So criminals know about this rule. It's a very simple one. And so in order to avoid detection, what they'll do is they'll break up that $10,000 transaction into multiple smaller transactions and sort of space them out time-wise, because the rule works so that within for example, like a day, if you do more than 10,000, they'll flag you. But, if it's in a week, it depends. Banks are different, but let's just say they're only looking at a day. Then you can just wait it out and deposit $5,000 today, $5,000 tomorrow. But if you're in a hurry, you can just deposit below the threshold, so $9,999, for example. And this is called structuring. And if you do get audited and the IRS sees that you were using structuring, then you'll get into a lot of trouble, so don't do this. So back to how machine learning could help. So hypothetically, what you could do is, let's take all those transactions that are not getting flagged and pass them into the algorithm and ask the algorithm to identify structuring versus non-structuring. And again, we were going to tell the algorithm what structuring and not structuring looks like in order for it to learn. Similar to teaching a child about animals. You tell them what the animals are, and then they can identify them because they've seen the answer before. And so just to finally reinforce this a little bit more, with machine learning algorithms, you don't have to specify the thresholds. They will actually learn it. It can notice trends and spikes over time because you're going to pass in features that contain maybe last week's transactions or last month's transactions going back 6 months. And the most important thing is that it's easy to retrain. So instead of having all these hard-coded rules that you then have to tweak, and I don't know how long that would take, you can just feed in new data and let the algorithm figure it out. So this comes to the point where in order for the algorithm to do a good job, you have to give it good information. And part of good information is what's called features, and you can develop them in a way that's helpful for the algorithm. So since we're thinking about banks and accounts, you would want to pass in features that provide context. So how much is in somebody's account, what their current balance is, how many deposits they made, what are their withdrawals like, what's the age of the account, how many linked accounts are there. And then if you want to have something a little bit more complicated, going back to the idea of encapsulating time, you could develop features that give you what happened last week from the transaction that you're looking at, and then the week before that, and the week before that, and so on for an entire month, right? And so this is just an example of that idea. Imagine your calendar. It could really start any day of the week, but we're going to just start at the top, and you can see that this person deposited $2,000. Then they didn't deposit any money, and then all of a sudden they start depositing $9,999 for about 5 consecutive days, mini break, and then again. So this would give the algorithm an idea of okay, that looks suspicious. I'm going to break off my threshold in between. And this is the same idea. So you'd actually want to provide, in addition to the deposits, you also want to look at the withdrawals. So here you see somebody deposited a bunch of money, and then at the end of the month, they withdraw $9,000, and again, that would be below the threshold that the rule wouldn't capture. Another feature that might be helpful for the algorithm is the idea of how much cash are people working in. So restaurants, for example, that are working entirely in cash, they're not necessarily going to be doing money laundering or structuring, but they have the ability to, right? Because everything's in cash and they can write their own books. So you could tell the algorithm a feature where you say, this is the percentage this account has that's dealing in cash this month, last month, and so on. And if you want, you can also design features. So maybe you have some intuition. You know that people are doing weird things with their taxes around tax season, so at the end of the month. So you add extra weights to any transaction that happened, for example, around November, December. And this is just an example, but you're allowed to add intuition into algorithms as well. So then the point here is, if you remember back to the random forest, so there you have a bunch of small decision trees. And within those decision trees, there are actually specific splits that happen. The algorithm figures out maybe that it's really important to break people up into those who spent more than $2,000 and those who withdrew less than $2,000. In addition, you can add feature interactions. The algorithm will figure out, like, okay, let's look at everybody's current balance, split them up, and then within that split up group, let's look at everybody, like how much they withdrew in the last 7 days. And then the final point is that with rules, you might be looking at 1 or 2 features, but with an algorithm, it's actually looking at all the features, and it's using all the features together to identify suspicious behavior. And the idea is that maybe you don't have, like, individual features won't actually identify a person as doing something suspicious, but all together, they give you a pretty good image. And then just like a nice bonus with machine learning, you can actually get feature importance. So when you're trying to figure out what features the algorithm used, H2O, for example, will give you back this nice chart, and it'll tell you that the feature that it split on the most and that minimized the prediction error the most is like total amount deposited. And then maybe you see, okay, well, the account holder's name's not useful. So putting it all together, in the example I showed before, you could pass in, transactions below $10,000, but you could actually pass in all the transactions. And then you could use your algorithm, whether it's a random forest or a GBM, and ask it to label structuring and not structuring. And if if 6 months go by and you want to have things verified, you could actually have analysts look at it, verify how it's doing, do a couple run-throughs, and then finally put it in production when you're feeling pretty good. And then 6 months down the line, just repeat the whole process. So basically, machine learning is great. It can help you enhance rules. It can generate better rules. It can identify new criminal patterns. And it could eventually replace rule-based systems. So just a resource page for H2O. If you want to use H2O, you can go download it on the webpage. We have a documentation that's pretty helpful. It's a little bit hard to find, but if you get to the documentation page, there's a user guide button. You can go ask questions on H2O Stream, which is our Google community page, and then there's Stack Overflow. And then don't forget to file your taxes. All right, that's it. Any questions?
In training, is there like one in the end that says these transactions were actually crooked? Like, did someone kind of end that at some point?
So the way that it would work is so somebody has to hand label it. At least in a supervised learning situation, they have to label it. And then you actually pass in the labeled answers to the algorithm. So you can think of it as like the algorithm has actually seen all the answers, and now you're giving a new question, and it kind of looks at it and says, like, have I seen this before? Yes. And what happened in that context? Okay, that person looked suspicious last time, so I'll label them as suspicious.
So if someone's like come up with a new way, or they're cheating rather by selling the house for $100 million when it's $30 million, like that doesn't get in.
Well, so if somebody has done something like that before and the algorithm has seen it before, then it would notice it. But that's also the point of retraining. So maybe what you do is get new labels and then retrain your algorithm and help it identify new patterns that way. But it does have to know what the answers are at some point. Yeah. Yes?
I remember in some of the diagrams you had mentioned the structure and not structure. Can you repeat again what that's a reference to?
Yeah, so structuring is just a method to do like illegal things, and you can use structuring to do tax evasion. Yeah. So structuring is when you take a $10,000 transaction and you break it up into smaller amounts so that you don't get notified, or you don't get yeah. Okay.
Are there any rules around the transparency of these models? Because one of the challenges with black box models, so you get variable importance, but you can't really isolate what actually is out.
Yeah.
You can't get it down to, it's $9,500. any regulation around being transparent and telling someone why they audited?
Yeah, yeah. There definitely are regulations, and a lot of times the reasons why certain machine learning algorithms aren't implemented is because regulators need to understand how they work. The nice thing with random forest is you could technically print out all the trees that are built and look at them, but there are also nice things like there's a package called Lime that helps make models become more interpretable. So it's definitely a challenge, but I would say that tree-based models are less black boxy than they seem. Yeah.
On the subject of retraining, are you familiar? There's a couple of dynamic screening models for trees. There's Amazon has their AppCut algorithm, and there's also that's random. There's also like a half space one that's also developed. Have you ever heard those and opinions on them?
I have not. No, sorry.
I don't think they'd be listed on Maybe.
Oh, okay. Okay. Yeah. Anybody else? Yeah.
So you're predicting transactions that look suspicious rather than ones that are actually fraudulent. So why not go all the way and just try to identify ones that are fraudulent?
You can, yeah. So the way that for the bank reports, they're actually just flagging it and then send it to the IRS, and then I guess the IRS, when they audit people, they can look it over and see whether it actually is tax evasion or structuring, but it's not specifying what it is. But with an algorithm, you can label it however you want. If you want to take the time to figure out exactly what tax evasion looks like and say this is tax evasion, the algorithm can learn to spit back tax evasion. Is that?
Yeah, that's what I was.
Okay. Yeah. Yeah.
Yeah, compliance officer. That's why applying it to them. That's their job.
Yeah, I don't know if anybody knows, but I think somebody was mentioning that there's all these reports that get sent out, but the IRS doesn't necessarily do anything with them. It's just if they do audit you and then they look at your sort of transaction history and they notice you've been doing something funny, then you're in a lot of trouble, right? Anybody else? All right. I think Ashraf, you're up.
Yeah, we'll do a quick 2-minute break to change presenters or strength or bathroom break.
So I think the person was talking about random cut forest.
What's talking about what?
The guy who's asking about Amazon.
Yeah.
He's asking random cut forest.
Random cut forest.
Random cut forest.
Cut forest.
Yeah,
Okay.
the way they do it is you run all. It's not that much. The way you do it is you run. Jeez, come on. All right. Let me stand here. This is a good place to stand. You gonna call? Go. Hi guys. Good evening. I guess you guys know that I'm the second speaker because I'm standing here. I'm supposed to be presenting something. So my name is Ashwath, and I'm actually a security scientist at H2O. I design algorithms in cybersecurity, financial fraud, and anything that involves anomalous behavior. And today, one part of the presentation was, which Lauren actually presented, is a specific use case. What I'm going to be talking about is how we go about implementing these use cases across different organizations due to different needs and purposes, problems, issues that they have. So before I go ahead, just a quick check. How many of you guys have used H2O? Okay, good. That's kind of good number. How many of you guys actually have implemented something with H2O that's actually running, let's say, somewhere? Oh, great. Okay. And how many of you have worked on anti-money laundering? Or are? Oh, okay, that's a pretty good number. So, okay. So one of the wait, did someone say something? So one of the first things that you come across whenever you're trying to implement a machine learning model across an organization where you need to work on AML is there is old school rule-based system, and if you have to implement machine learning, you can't necessarily replace it because there is rule-based system is something that regulators accept. It is something that they like, and they're comfortable with it. You're going there and you're almost upsetting them, so you don't want to be doing that. So the process that we take is we actually are in a position where we can design deep learning algorithms which is purely data driven and things like that, but you can't necessarily say for that $1 million tool that you have and come and stick with this which is open source and free. That's not how we can go. So there is this process that we go about, which is like a rule-based approach. Then we design it's a purely feature-based approach, which could be like a tree-based model, and then it's a pure data-driven approach. So the issues with rule-based approach, I'm sure most of you people who work on AML kind of know, is that you have alerts that come out of systems, like Fiserv, Actimize. I believe there's one more. Kind of losing out the name right now. So you have alerts that come out, and these alerts are basically generated when transactions and account information is actually passed through these systems. And this is actually a batch process. So what happens is there is a simple cache that exists in these systems, and this has limited amount of memory. So let's say last week you did a transaction which is more than $10,000. Okay, that gets tagged and it gets cached in the memory. And if this week again you do something that's 10,000 and above, then that's grounds for some kind of money movement that you're doing. So that gets stored in the memory and it gets compared, and then a SAR gets an alert gets generated, not a SAR yet. It's a very simple process. So you have close to about anywhere between 50 to 200 rules, depending on how many different lines of businesses that you have, how many different kinds of customers that you support, and how many different interesting behavior that you want to catch. So that's the basic structure of how the rule-based algorithm works. And what happens is once the alert is generated, there is an investigator who is actually sitting and looking through these alerts. He goes through LexisNexis to find out if you have any criminal history. Trust me, the moment you have criminal history, you're already at the other end of the system. You're like, they're ready to flag you. They just need one more set of information to flag. It's that easy for them. And they go through your account databases, transaction information, your card information. They actually Google you as well. So just to find out, what do you do, which is a very interesting way they do it. They actually have a lot of info. They have a lot of experience with regard to the AML, so they are a good set of people to work with to learn, the kind of intuitions that Lauren was actually talking about to actually bring it into a feature set. So that is actually a good set of people for us to work with. I'll come to that a bit later. But right now, what they do is they look through your alerts, manually separate the ones that look suspicious and the ones that don't look suspicious. And what happens is sometimes, you would have done, you would have never done, a transaction that is that's worthy of being identified as, let's say, something criminal, and they would have probably seen a couple of these transactions that has come out. So then they'll actually upgrade you to, like an intermediary alert, something above an alert, which basically means that this might need a bit more investigation. And then, when a senior investigator goes through it, looks through your data, and then he could upgrade you to, an actual alert, an actual SAR, or, say, okay, this is just a one-off case. We don't need to flag this person. So that's the usual process how they go about this. So some of the issues with this, it's an extremely manual process. The data sets, are everywhere. You have some people running on DB2, some people running on Oracle, data sets on Hadoop. The data sets are very dispersed. You don't necessarily have access to it. The average time that someone takes to go through from, looking at your alert to investigating you is, it easily ends up between 40 minutes to about 2 hours. So you're losing a lot of time, which you could probably encode in an algorithm and get decent results. Sometimes the output is very inconsistent and due to the nature of the alert itself. This is very evident in the fact that a lot of alerts that gets 80% of the alerts that actually comes through, is actually false positive. So every rule-based system that generates alerts, actually 80% of them is a false positive. And when I say 80%, that's actually the best number we have seen. We've seen banks that have 100% false positive. I don't know how you achieve 100%, but they have that. I guess you get, those people are not there in the audience, I hope. But anyway, you could do that as well. And so as I said, it's extremely subjective. One of the reasons for that is a lot of these banks take these as an appliance and they install it. First of all, AML is a cost center for most of the financial organizations. It's not a revenue generating thing. It's not something that they love to do. It is something that they have to do. So what happens is, it is this appliance that they place in, and they don't necessarily work on the rules. They don't necessarily work on the features that go into these rules, because that's an add-on investment on top of the $1 million appliance that they already have. So they never customize these rules for their needs, which is one of the reasons you get tons of errors and things like that. And I guess the banks are taken to put a ride at those things. So that's kind of how how the rule-based system goes. So the way we do it is we work with the system. As I said, we don't want to upset the whole thing. So what we do is we come up with a set of features with a feature-based model that kind of works in parallel to the rule-based system. It does not replace the entire thing. And for structuring, we heard earlier some of the features that come by. So the advantage of features, the idea is that features are actually the metadata that comes out of your data. Now, for example, you could say, oh, I have tons of data, and I believe that every organization around here would probably be capturing every data that they have right now, because storage is cheap, and Amazon gives you Glacier storage for like, I think, point something cents. So everyone wants to store it on Amazon. So storage is cheap, so you'll never throw out anything. That's like data hoarding. And then what you want to do next is you have machine learning. Now you want to use your data and combine machine learning together and say, okay, let me get something insightful. It's not automatic. What you have to design is you have to design features. You have to come up with features that actually make sense, that pull out those specific aspects of data and say, hey, this is a feature that is bringing interesting aspects of your data out. So take it and learn it, kind of a thing for the model. So which is one of the reasons we consider features to be like the metadata of the data itself, which gives you information. And as I said earlier, they help the algorithms understand what the data is made up of. You could look at features also as a form of translation between the data itself and the algorithm. It's where your data is made interpretable to an algorithm. So which is one of the reasons feature engineering, I think, is a really very important aspect of designing algorithm, regardless of AML. I mean, anything that you do in machine learning, for that matter, feature importance is very interesting and important as well. And so the sources of data that we use, this is actually a minimal list of sources that we use. Transaction information, account information, and alerts that comes out of systems. primarily because a lot of financial organizations that we work with don't necessarily have card and wire data because that gets routed through different, different other financial institutions. So they don't necessarily have that. So sometimes we actually have to stick with this. Sometimes we tend to get a lot more information, with their card, wire, asset information and things like that. So that kind of helps us augment a lot of data and features. I kind of forgot to say this earlier in my talk, but if you have any questions on any slides, stop me right there and you can. Do I try to, yeah. Yeah. No, so the way we do it is we actually identify transactions, which could be malicious, and then we see if the account itself shows a behavior. So it's not completely, probabilistic. It's there is a sense of, go from transactions to accounts. Yes. That's actually a super question because that is exactly what I'm working on right now. So in the future, yes. Thank you. Yeah. So one of the things that we do is we very deliberately avoid looking at what the feature in the rule is looking and what the feature in the rule is. For example, the variable in the rule. I shouldn't say feature. Let's separate these two spaces. And the reason is we are targeting the the end result of the rule. For example, structuring, right? Structuring could be 2,000. You could be breaking down $2,000 amounts and then moving it across your account. That will never get flagged. But if it's 10,000, just around 10,000 or 10,000 and something, then it could get flagged, right? So we kind of avoid the idea of the variable itself and see what are the other encompassing behavior that can exist. Yeah. Yes, we do. Yeah. Yeah. So sometimes what we do is we see how how much of a weight a certain variable provides for us, and then we bring it in. Sometimes we do take the kitchen sink approach, where we have a lot of features that we have designed, and we want the algorithm to tell us what is the order of. No, we do. We check that. So it's two different approaches that we do. Sometimes we check the feature correlations earlier, but so the last piece of work that I did, we had about 450 features. So looking at correlations between 450 features is a bit difficult for us. So what we did is we ran the algorithm. We got a set of the feature priority from the algorithm, and then we said, let's now look at the correlation to see how important they can be. So. No other questions, I hope. Yeah. So we use three different, at a minimal level, we use three different sources: transactions, accounts, and alerts, to get to a point where our algorithm is actually usable for anyone. And so one of the features that we look at, so I actually come, my entire grad school was with the idea of rolling features. So I'm very biased towards designing rolling features, where you're looking at behavior for like every 7 days, 3 days, 4 days, and things like that. Because that's how it's, in malicious behavior, rolling features are extremely important, regardless of what field you're working in. So which is one of the reasons a lot of features that I design are actually based off like what is happening in the last 7 days or the last 180 days or the last few hours for that matter and things like that. And these features actually help us a lot in terms of how when we design features. They are helping us identify every small aspect of the behavior itself. For example, in a rule-based system, your rule is literally waiting for that one spike. Oh, is it 10,000? Is it about 10,000? Yes, no. If it's not about 10,000, that entire spike is dead for your system. you can never identify that there is actually, a malicious transaction that happened. But now, if you design a rolling feature, what happens is you are averaging that 10,000 across a period of time. So now what you're doing is you're telling the algorithm, hey, learn as this feature grows and learn as this feature, goes down. So it's kind of giving it's normalizing that one peak, which is actually very good, because what that means is that machine learning algorithms tend to learn when there's a lot more probability of a certain transaction or a value or something like that. So when you break down that one spike into a huge, a time series or something, the algorithm is reinforced again and again that, okay, this is a good thing to learn, and so on. So that feature actually becomes important. So anything that shows interesting spikes, for that matter, one single spikes, actually gets captured across as a time series, with something like this. So this kind of helps for us. So we have LSTMs. We actually try to do the same thing with RNNs, but the issue with LSTMs is you can't say how far how long ago do you want the memory to be retained, right? So there are interesting aspects of the memory that you can retain, but you don't know what it is actually capturing from the system. So one of the things that we try to do for that is we try to provide feature weights to say that, this is probably a more important feature for you to cache it or something like that. And we have had some success, but we've actually had more success with our tree-based algorithm. So this is actually like one of the examples of features that we design, which helps us capture certain spikes. So the advantage of features are, features tend to highlight aspects of transactions, and because they continuously track an account, it's kind of reinforcing for the model to say, hey, look at this. This is actually really good for you to learn this behavior. And this is definitely much better than rules, because rules are just looking at one specific spike, and if the rules miss that spike, you've completely lost your signal. So it's always a game, a play between how do you want to capture your signal and how do you want to kind of reduce noise. So this is the implementation of how the H2O algorithm works. So what we do is this actually runs completely in parallel to the system, to the existing rule-based system. What we do is the same set of alerts actually goes through the H2O system. We read through transactions, accounts, and cards, and etc. Different kinds of data sets, and then we spit out alerts that could be suspicious and not suspicious. Now what happens is this actually all these alerts, mind you, have already been sent out by the existing systems in a financial institution. So we're not doing any additional work. All we're adding is, for each of these alerts, we're adding an additional tag saying the machine learning algorithm flagged this as a yes or a no. And when the person investigates, he's actually reinforcing whether the algorithm was right or wrong. So that kind of helps us learn very quickly. So that helps. Yeah. So actually, that's probably the next slide. So the investigator actually helps us, reinforce the algorithm. And so the advantage of the feature-based model is use artificial intelligence. I think everyone likes artificial intelligence now, because Elon Musk kind of runs with it. So and the features are very consistent. It's a very good approach, very consistent, mathematically, statistically proven. Sorry, not proven approach, and it's a quick way to classify. This kind of reduces a false positive to a good extent. Now, the false positive reduction is always based off your financial institution risk capital, because we have seen across the board, where we have set the thresholds for different organizations at different levels. Some organizations do not care about how much of a false positive reduction you can give them, but they care about a really small number in terms of false negatives. They don't want to lose out on the ones that they could, be false negatives. Do you have a question, Bill? Yeah. So, please, yeah.
Your model doesn't
No, this is a false negative after the alerts. So this is what you have to understand here is that the entire space of what is a ground truth is post alert, not in the transaction space. So, for example, you
basically you're saying there are like thousands alerts.
Yes. Yeah. That's the false negatives. Yes. And
stuff that wasn't flagged by the rule-based system
will never get seen by anyone. Yes. Yes. You might want to wait till I go to my deep learning algorithms. So this is the method that we use for basically reinforcing our the decision that we make on our alerts. So the investigator actually goes through all the alerts, and the algorithm gets reinforced to figure out if it's actually a good or a bad thing that based off our decision. And then there is a retraining loop that we have for the algorithm, which constantly retrains. If the algorithm falls below a certain threshold, or if it's like a day old or something like that, the algorithm tends to retrain, based off the new data set that we get from the investigators. So this is the current model that we have that is actually implemented, which is a feature-based system. So what we do is, the advantage here is that analyst feedback actually helps us, and the analyst actually has one unified interface in this case. Along with this, we also ensure that the analyst is able to capture all the data that he needs. Other than Google and LexisNexis, I think the rest of the data set we kind of integrated. Yeah. No, please. We do, yes. Yeah. So the type, you're talking about the typologies, right? Yeah, we do. Yes, we actually consider that, and we've not seen. So we actually have families of typologies in the sense, you have like structuring a certain kind of money movement and stuff like that actually gets together. Then you have, for example, maybe terrorist financing, which could fit with structuring in a different way, or you could have that with sleeper cell accounts kind of in a different way. So we have a relationship between how these two work. At least we know kind of how the relationship between these two works. So that helps us identify, if it's in the same family or if you've completely missed the ball and it's something else out there. And so yeah, so the analyst actually gets to see the entire data set very quickly. It kind of saves time, for the analyst as well. So you're not doing a 40-minute thing anymore, or a 2-hour thing for that matter. It's actually smaller than that. So reduces time, for a financial institution, the amount of money you spend on it. So the final one is basically the pure data-driven approach that we are working on. And the idea here is what you actually mentioned is that we could not capture false negatives earlier, which were not coming through alerts. But the idea here is we don't take alert data anymore. We purely take transactions, and everything else, and we basically design the algorithm in such a way that we are able to identify malicious behavior, without needing a flag. Without needing a flag in the sense, without needing the alerts. And so this is in the process we're designing right now. We've got some success, probably not as close to as what we want, or probably not as close as the 3 algorithms. But yeah, we're there. And the one of the general reasons why we wanted to avoid the alert data, the alert itself, is because if you start building systems that are smart, then the bad people tend to become smart too. Actually, they're always better than you. They're one step ahead of you every time. So you want to be able to think of this problem as an anomaly detection problem, more of an anomaly detection problem, and less of a classificational based off a certain group or a certain family problem, and which is where actually this approach helps us. So this approach has got some amount of unsupervised classifications that we do, and then some amount of supervised, based off probabilities that we try and classify what if it's suspicious or not suspicious. So yeah, the idea, at least the approach here is that the algorithm very clearly understands, what malicious behavior is, and the other idea here is also that you need not use as many features as you could be probably using in a tree-based model, because here we expect the data itself to be able to express the kind of behavior that comes through it. So that's one of the things, and because we don't involve alerts anymore, so there is no alert training that's required. It's not a parallel pipeline that needs to run, and as I said, it's more of an anomalous behavior problem that we have here, and you've got much deeper insights about your customer, because deep learning algorithms tend to have a good way of looking at data across time spaces. So that's a greater way in which you can look at data. So yes, thank you. And any questions? Please.
So it sounds like a lot of this is assignment. Do you ever wish you could aggregate all of the banks high level?
So we actually work across banks. So it's not just like one financial institution. We're working across banks. So one of the things that we do see is we do see behavior that could be happening somewhere else, and then we have a better insight about the transaction. Yes, sir.
Recently there was something called Panama Papers.
Yeah.
So that was apparently some kind of coup. So why was that not detected by machine learning?
I don't think anyone was trying to deploy machine learning algorithm to identify that. I don't think there was any kind of.
So they
yeah.
had control of that, and they said no.
Yeah. Yes. That's actually a good question. So the way we run it is we run it in two ways. At least that's what the system that we have designed runs it in two ways. Is that you'll have to have some blind test, where you don't necessarily know what the investigator is running, because you don't want the investigator to get biased every time H2O says this is a good thing, right? Or a bad thing for that matter, because that will affect you in a different way. So we have a sampling where it's a blind test. We have a sampling where it's not a blind test. And we also have tests across different geographies, because different people have different, biases, understanding about the behavior and things like that, different times of day. So that's how we make sure that at least it's. So on an average, the banks that we've worked with, the number of investigators could be probably about 130 to 250. So you're looking at roughly about, about 200 investigators. Yes.
Most knowledge systems end up changing, or I think for the intermediate reference,
so
when I try to break these systems, I train them to expect the steady state behavior, which is actually legal.
Yeah.
So that they're trained with more.
So the thing is, if you're trying to do something anomalous, let's say outside the box or something.
I define anomaly relative to my normal operation or average.
True. So
how do you define the anomaly?
So there are two ways in which you do that. One is the family you belong to, and two is based off like your transactions. So when I say your family, for example, as a customer, let's say you were doing commercial banking or you're doing personal banking. So you largely belong to the personal banking family. And your data is, so whatever we compare, it's usually normalized and we see, how far apart are you from a certain curve, if you actually match that or not. Now, that is one way of identifying if you're part of the family. Now, but that is just a mere weight that we get from that family. The moment you don't match, let's say the standard deviation that we're looking at, you are given a weight. You're not classified as anomalous yet. Because the other thing that we also look at is we also see the kind of transactions that you do. So it's actually a captured weight across different features, which would be the family.
I can structure my transactions.
True, yeah. True.
That's actually what we do.
True, yeah. I mean, but the way we do it, but the way we try to avoid that is we try to keep the, we try to see that the difference from you and the family is as minimal as possible. Even if there's a minimal difference from your family, you flag. Hey,
I'll give you an easy to understand example. You know you're going to do money laundering in the future, and before you do that, make sure that artificially 99% of all your transactions are cash.
Sure.
By making fake transactions that are perfectly legal, you just loop it back to yourself, so that later on you're in the bucket of people who have 99% cash transactions. Well, that's why I was asking about the graph.
Definitely, yeah.
If you don't do that,
we're not there yet. It is, yeah. I mean, I can very clearly tell you that it's not an end all. We know how to catch you kind of a thing. It's always a cat and mouse game, so which makes it fun. So when you say the vast majority, you're right. So the issue there is the minimalism in the signal, or the limited signal that we get. So what we actually have to do is sometimes when the signal is really limited, we actually manually break down groups in terms of the kind of cash transaction that you're doing. But we also see that a lot of people tend to do who don't do money laundering tend to fall in non-cash based or non-monetary instrument based transactions. So which kind of makes it easy for us. Earlier we used to partition the space. We don't necessarily do that anymore because of the kind of instrument that you use. Okay, yes, thanks.
So that ends our meetup. We'll have a recording and the slides up in about a day. If anybody's interested in talking to us, we'll be here for another 15 minutes. Or if you want to speak at our next meetup, please let me know. Thank you.